Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back. Today we are going to continue with our unfinished discussion on plate tectonics to begin with, and then we are going to move on to look at a few important characteristics of earthquakes. Now let us get on with the objectives of what we want to try to accomplish at the end of this particular lesson. At the end of this lesson, we would like to be able to list the features of converging and diverging plate boundaries. We started looking at this aspect in the last lesson itself, and we are going to continue and complete this discussion. Then we would like to be able to describe the evolution of continents. This is also really an unfinished objective of the previous lesson, continuation in fact of the previous lesson. List the types of seismic waves and describe their characteristics. This is a new topic, and describe the measures of strengths of an earthquake. So let us move on with the continent to continent convergence, the third type of convergence which we want to look at. We have already looked at the convergence between an oceanic plate and a continental plate, and as well as we looked at convergence of two oceanic plates. Now here what we are going to look at is convergence between two continental plates. One of the examples of this type of convergence is the Indian plate colliding with the Eurasian plate, and the plate boundary where that is taking place is the Himalayan mountain ranges. And also there is another example for this type of convergence, and that is in the southern part of Europe, where again there is another very important mountain range which is the Alps. Now this type of convergence actually begins, as you can see on this particular cartoon here, as a convergence between oceanic plate and a continental plate. So in the cartoon shown here, the section shown here, basically you can see all the features that we have already discussed when we were talking about the convergence between an oceanic plate and a continental plate. So here what you have got is the oceanic plate on your left and the continental plate on the right, and you can see here the accretion zone shown by cross-hatched brown jagged areas near the right corner underneath the ocean, and then you can see the volcanic volcanism which is typical of oceanic and continental convergence between oceanic plate and continental plate towards the right end of this particular section. And as earlier, a subduction is taking place where the oceanic plate is actually moving underneath the continental plate. You can see what I tried to do here is to maintain the same type of color scheme and hatching scheme as we have discussed near the end of the previous lesson. In that, the lithosphere is indicated by a green and yellow scripted, actually green and orange scripted layer, whereas asthenosphere is indicated by flat orange, deep orange layering, as was done in the previous cases. And the direction of plate movement is shown by thick brown arrows, and that is also the same type of symbol that we used when we discussed about the convergence between two oceanic plates and one continental and one oceanic plate. So, as I mentioned, that this particular convergence begins as a convergence between an oceanic plate and a continental plate, and then basically what happens, the ocean starts getting squeezed. The distance or the area which is covered by the ocean, it gets narrower and narrower as the continental mass towards the left starts moving further to the right, and the what happens, the outcome of that is that you can see that the zone of accretion actually starts piling up. Actually, it becomes higher and higher, and the margin of the continental plate also starts piling up. Another thing you should notice here, as well as in any ocean to continent convergence, is the trench that develops near the location where the oceanic plate starts subducting, and that is because there is a frictional locking really of the continental plate near the shoulder, where the dip of the oceanic plate suddenly starts to increase. In what happens actually there, because of the locking, frictional locking, the continental plate is really dragged down a little bit along with the subduction of the oceanic plate, and as a result a trench generally develops near the location where the oceanic plate goes underneath the continental plate, and that particular feature is called a trench. And in fact, there are examples of very significant trenches near the margins of oceans, such as the margins of the Pacific Ocean, near the islands of island chain of Philippines. There is a very deep trench called Marianas Trench, and that is in fact one of the deepest features on the surface of the earth, where the depth of the trench is in fact greater than the entire height of the Himalayan mountain range. Okay, so now we continue with the discussion on continent to continent convergence. Here the continental plate on the left starts moving to the, actually is moving, as you have seen already, to the right, and the ocean mass, the area underneath the ocean has squeezed, has become smaller as a result, and finally what happens, the ocean is going to completely is going to get eliminated totally, and the area between the new continental plate, between the continental plate on the left and the continental plate to the right, the shallow water bodies, they get readily filled up with sediments, and that is indicated here with a gray hatched block in between the plate on the left near the center of this particular cartoon. Actually, you can see also you should one important feature to notice here is that since continental plates typically are of similar density, the subduction action of the continental plate, one continental plate underneath the second one, it gets muted. It does not want to go down underneath the other continental plate, and what ends up happening is really sort of a head on collision between the two continental plates without any significant subduction. As you can see here, is that the deep subduction what we saw in the previous cartoon is absent in this particular cartoon, and what happens, the collision of the two continental plate gives rise to the pushing up, actually pushing up of a significant mountain chain at the boundary of the two plates, and that is indicated here in this area, where the continental plate on the left is coming and colliding with the plate on the left, on the right actually. So this one is one plate, let us call it plate 2, and this one is plate 1, and in fact the collision here is almost like a head on collision with very little subduction in this area, little subduction action. And a mountain chain starts building up because of the collision, and the height of the mountain chain keeps on rising as the convergence progresses. Okay, so this is the process basically of continent to continent convergence. And as we have seen an example, a present day example of the mountain chains that develop as a result of continent to continent convergence is the Himalayan mountain chain as well as the Alps of southern Europe. Now, what I want to stress, what I want to emphasize at this point is that you should realize that there is a huge change in the stress regime near the plate boundaries because of the convergence activities that goes on, and this particular change in stress regime does indeed lead to failure of large blocks of rock, and the outcome of that particular outcome of that failure of a large mass of rock is essentially an earthquake. So what we see is that there is a preponderance of earthquake activities near the plate boundaries. That is not to say though that all the earthquakes that have been recorded so far take place along the margins of plates. There are earthquake activities near the middle of continental plates, and we are going to look at the details why those kind of earthquakes happen or occur later on in one of the future lessons of this course. We have got one more thing to consider here, and that is the process of divergence. Basically, divergence takes place near where magma plume comes and daylights near at the surface of the earth, and that typically takes place where the thickness of the plate or thickness of the lithosphere is minimum. Typically that happens near mid oceanic ridges. We are going to look at some of the examples in the next slide. One of the examples I have already shown in the previous lesson, and that was the example of mid Atlantic ridge. That is an example of a mid oceanic spreading center. Then there is another one that is a continental hotspot, really, middle near the at the middle of an existing continental plate, and that is the East African Rift Valley. We are going to look at both of them, the locations of these features in the next slide. But before that, let's look at the features associated with a divergent boundary. What happens here is that the thickness of the lithosphere is really very less, and as a result magma is pushed, it gets pushed to the surface, and as it pushes it moves the existing rock laterally away from the spreading center. And you can see that in this particular cartoon or section, vertical section, where thrust faulting takes place. Actually, it is not so much of faulting because of the great elevated temperature regime at which this particular thing goes on. This type of divergent at the divergent boundary, the temperature is so high that the rock really, even in the lithosphere, it is quite ductile, and as it gets pushed away from the center of spreading, it cools off and solidifies. And because of the fact that because of the ductility and because of the lack of thickness of brittle rock available in this area, basically what we typically see is that near spreading centers, whatever earthquakes take place, they are of relatively much smaller strength than the earthquakes that occur near convergent boundaries. Now, these are the features really associated with a divergent boundary, and that could be, as I said, at the mid-oceanic ridge or at a continental rift valley, active rift valley, as we are going to see in the next little bit. So here, this is the magma chamber, as is evident. This is the magma chamber, and magma gets spewed out, and that spewing out itself actually triggers the lateral movement of the continental crust. And as earlier, this one, the orange shaded area indicates asthenosphere, and this one, the thickness, this thickness here is the crust or lithosphere, really. This is the lithosphere. All right. So that actually takes care of the plate boundaries. There is another type of boundary, as I have already mentioned, and that is called transform boundary. And as I have indicated in the previous lesson, is that at transform boundaries, one plate slides past another, and there is no subduction, or no subduction takes place. No reverse faulting takes place. Basically, reverse faulting or normal faulting takes place, and an example of such type of boundary is near the southwest coast of United States. Now, I want to, before I quit this particular slide, I want to mention that at the spreading boundary, basically what you get, I want to emphasize this point, is that at the spreading boundary, typically the earthquakes are much less severe than the earthquakes that are observed at the convergent boundaries. and in fact the largest earthquakes that have been recorded do take place near the area where an oceanic plate is subducting underneath a continental plate. All right. Now this particular map, this has been taken from NASA. This particular map actually shows all the plate boundaries of the Earth, and we have seen these plate boundaries earlier, but here we look at the plate boundaries in the light of what we have learned so far after we finished the convergent, divergent and transform boundaries. And here all the different plate boundaries are separated, color coded separately. So the red coded plate boundaries here, such as these, such as here, here, and here, they represent spreading boundaries where ocean floor is spreading apart, and the researchers have also estimated a rate of spreading. So, for instance, the spreading rate at the East Pacific rise, this one here is the East Pacific rise, this one here is the East Pacific rise, that is very the feature, I mean the boundary, the plate boundary here is very similar in nature as the Mid Atlantic rise. East Pacific rise is this one, and this one here is the Mid Atlantic rise, which we have looked at earlier. Now the rate of spreading at East Pacific rise has been estimated to be about 15 centimeter per year, and that is one of the largest spreading rates that has been estimated anywhere on the surface of the Earth. In comparison, the spreading rate at Mid Atlantic rise is about 3.5 centimeter per year, 3.5 centimeter per year. Now, so those are the spreading boundaries, spreading centers, and then what you also can see on this particular slide is that there are blue coded plate boundaries, and these areas there is a convergence going on. One example of that is the northern boundary between the Indian plate and the Eurasian plate. So this one here is the Eurasian plate, and the Indian plate is here. So this is the Indian plate. So you can see that there is a convergence because of the fact that the Indian plate is moving up towards the north predominantly. As a result, there is a converging boundary at the top, at the north end or the northern margins of the Indian plate. There is a similar converging boundary along the west coast of South America and along the margins of the Mediterranean, as we have already seen. Now, I also want to indicate at this on this slide, I want to highlight on this particular slide is the mid-oceanic or rather a spreading center along the eastern part of the African continent, and this is called the East African Rift Valley. Here what is happening, a spreading is going on really in that manner, which is very similar in nature as a as the spreading center, as the spreading that take place near mid oceanic ridges. Now you can see some red dots. You can see red dots actually along the at many places on the surface of the earth. For instance, at this location here near the western part of the North America, at many locations there, along the African rift, then along the boundary between the near the archipelago of Indonesia. At these areas basically are the centers of volcanism, where the plate thickness is little bit limited and magma is actually daylighting on these areas along these centers. So these areas are called hotspots, where magma is getting ejected onto the surface of the earth. Okay, so these are the plate boundaries and different features that are associated with the volcanism at the plate boundaries and at within the intraplate areas. Now we can look at the history of the earth, or really how the continental how different continental plate they started evolving from very early on in the geologic history of the earth. I want to mention here is that what we are going to see, what we are going to look at is the evolution of continents, or the maps of the globe as we see, and what was the appearance of these continents way back in geologic history, and what would it be like in the far future. Now these inferences have been drawn from the idea of oceanic from the evidence, from the fossil evidence within the rock masses, dating of rock formations that are found in different parts of the globe, and these allowed actually rock masses to be correlated from rock masses within one continent to be correlated with that in another continent, which are relatively separated by a vast expanse of ocean or some other continental masses at the present time. And the rate of movement of the plates at the present time has been extrapolated, and that allowed us to visualize what the earth would look like, or what the continents would look like in far future. And that is what has been shown on these simplified maps. I got this information from information shown on these maps from USGS and from a project which has been completed recently, called the PaleoMap project. Okay, what is shown on this particular cartoon is how the earth looked like 650 million years ago in the Precambrian age. And on the right, you can what I have shown on this particular cartoon is a bar chart showing the names of different geologic ages and the boundary between, or geologic era really, and the boundary between these geologic era. For example, let me before I move on, let me explain that. Looking at the bar chart on the right of this particular slide. Archean age or Archean era is a 3000 million years long geologic era, which began from about 4500 million years ago, and it lasted until about 1500 million years ago from present, followed by Proterozoic that lasted between 1500 million years from now to 520 million years from now approximately, followed by Paleozoic between 180 million years ago and 520 million years ago, followed by Mesozoic, which lasted between 180 million years from ago to 60 million years ago. Then we have got Cenozoic, which lasted between 60 million years ago and about 1 million years ago, and the present geologic era is called the Quaternary, which started about a million years ago counted from now. So that is the bar chart, that is the explanation on the bar chart, which you will see on each one of these slides that are going to come right after this particular one. And there is an arrow, orange arrow on the right side of the bar chart that shows the timing, approximate timing of the map of the earth that is shown on the left. So the map of the earth that is shown on the left is actually the one in the Precambrian era, Precambrian era, which is approximately 650 million years ago. And at that age there was a supercontinent called Rodinia, and what you have got on the left of this particular map is Pan-African Ocean, and on the right is Panthalasic Ocean. Now look at how these continents are, how the continent breaks up. About 514 million years ago, the map of the globe looked somewhat like this. What you have got here is a supercontinent near the southern edge, southern periphery, southern end of the globe called Gondwana, and there were three continents a little bit further north: Laurentia, Baltica, and Siberia. And Laurentia really is the landmass which covers much of North America at the present time. So this is the map of the globe that was there in the Precambrian age about 514 million years ago. Precambrian, in fact, is a part of the Paleozoic geologic era. It is near the beginning of the Paleozoic era. What you got here is an ocean near the southwest called Iapetus Ocean, and you also have got Panthalasic Ocean as earlier. Then we look at the map as it looked like about 225 million years ago. You can see the formation of a supercontinent here, and this is called the supercontinent of Pangaea. And you can see the outline of the present of the modern continents. It started evolving, and you can see the outline of the South American continent towards the left, bottom left of this particular supercontinent called Pangaea, Africa to the bottom right, just east of South America. Then on top of South America is the present day North America, and Eurasia is further to the north and east of the north of to the northeastern corner of the supercontinent of Pangaea. This was how the map looked like in the Permian age about 225 million years ago, and again we are still in the Paleozoic era as in the previous slide. Now we move on to Triassic era, about 200, which is about 200 million years ago, and you can see the Pangaea, the supercontinent of Pangaea has started breaking up. We are still in the Paleozoic era, Paleozoic geologic era, and here the continents have started breaking up, as we have already we can notice here with the Laurentia Laurentian continent near the northern part, and Gondwana land. This is another supercontinent which is starting to build up towards the southern peripheries, and between Laurentia and Gondwana land you have got the Tethys Sea. Let us look at what happens further down in the Jurassic age. Which is near the middle of the Mesozoic geologic era. That is being kept track by on the bar chart on the bar chart on the right, and you can see here that the continent of Africa, you can see the outline of the continent of Africa and the South American continent. They are still together, but India has started drifting away from Africa. It is starting to drift north and east, and you can see here is that the Eurasian continent is still in contact with the North American continent. Cretaceous, 65 million years ago, and we are pretty much near the boundary of Mesozoic and Cenozoic geologic era, and you can see that Atlantic Ocean is starting to open up between Africa and South America, but the North American continent is still in contact with the Eurasian landmass, and India is still drifting further. The Indian plate is still drifting further to the north and east. The present map, India has already collided with the Eurasian plate. The Atlantic Ocean has opened up right from the North Pole to Antarctica, and let's look at what happens 50 million years ahead in future. Atlantic Ocean opens up even further, and what you can see is that the Mediterranean Ocean, Mediterranean Sea has closed up, and the continent of Africa is in contact, is totally converged with the Eurasian continent. And you should also notice that the Indian plate is actually sort of rotating in the clockwise direction from this particular viewpoint, and a part of also you can see a part of Indonesian archipelago is expected to converge with the continent of Australia. Then we look at 250 million years from now, a supercontinent will again form, and this particular supercontinent is given the name of Pangaea Ultima. And what you see here is that the Atlantic Ocean, it has closed, and the Indian remnant of Indian Ocean you can see here. It is just like an inland sea at this point of time, and the Indian plate looks like this. So what you have got here is a complete convergence of Africa, Eurasia, India, North and South America. All these land masses as they exist today, they are going to converge and form a supercontinent called Pangaea Ultima. So, what you see here is that over the geologic history, several different continents, they collide with each other, then they break apart and they coalesce again after and new at new converging boundaries. So, over this entire time scale, mountain chains are going to build up at the converging boundary between continental between at the locations of continent to continent convergence, and then when the continents spread apart, new spreading centers form, as we see from these series of maps that I just now presented, and new oceans starts forming, new oceans start forming near the spreading centers, along the spreading centers. So, you are going to expect that there are mountain chains that are going to evolve from all these continent to continent convergence, and oceans keep on forming as seafloor spreading at the spreading centers, across the spreading centers. And two such examples of mountain chains we can see right now, and they are the Himalayan and the Himalayan mountain chain and the mountain chain of southern Europe, the Alps. One of the mountain chains I want to mention at this point of time that covers a long stretch along the eastern part of North America, from southwest to northeast, and that is called the Appalachian mountain chain. And that particular mountain chain was formed in a very similar manner under very similar circumstances about 390 million years ago, when the continent of Laurentia collided with the landmass that we with another landmass that we saw in one of the previous slides. Let's run this particular slide once again to explain. When actually Laurentia collided with Baltica at about 390 million years ago, and at that time the mountain chain of Appalachian formed near the margins near the converging boundary, and you can see the remnants of that particular mountain chain right now in the eastern part of North America. Okay. So, we move on to the earthquake process with that knowledge. How earthquake is triggered? Earthquake essentially is triggered because of stress concentration within rock mass, because of plate movement, or because of other causes. And the other causes could be volcanism at intraplate locations, or activation of rift valleys at the center of pre-existing rift valleys, remnants of earlier continental features at near the middle of the existing continents. So these points of weaknesses could be reactivated because of stress concentration, because of the collision of plates, or because of volcanism, or any other reason, or even accumulation of huge sediment load. We are going to look at the details of these triggers in one of the future lessons. Then failure of rock mass after stress buildup occurs when the elevated stress cannot be sustained anymore. And what happens because of the failure, is a deformation occurs, a sudden explosive deformation occurs near the location where the failure is taking place, and the localized transient deformation propagates as actually the deformation actually propagates, the pattern of deformation propagates as a stress wave, and these stress waves are called seismic waves. We are going to look at the essential features of the seismic waves in the next little bit. And when stress wave propagates from one location to the other, then random movement of soil and rock is going to occur along the path of the seismic wave propagation, and straining of soil and rock is going to trigger ground failure. Straining of soil and rock is going to, it could trigger actually ground failure, or it could inflict damage to facilities constructed on or within the layers of soil or rock. Okay, we have to look at a few definitions in this connection. Now let us say the failure of rock mass is triggered at the location underground shown on this particular cartoon. That location is called the focus or hypocenter of an earthquake. Now if you project the hypocenter to the ground surface, then you are going to get the epicenter. That is the definition of epicenter. Now if you find the distance from the hypocenter to a site, then that is called the hypocentral distance. Similarly, if you compute the distance between the epicenter and the site, then what you get is an epicentral distance. Now let us look at the features, the characteristics of seismic waves. There are two types of seismic waves really. The waves, it is exactly similar to say for example, if you throw a pebble on a surface on the surface of water in a pond or a water body, then what you see is a wave is going to be triggered when the pebble hits the water surface, and the disturbance actually propagates radially from the location where the disturbance was originally triggered. The movement of seismic wave is exactly analogous to what you see when a water wave is generated, but here what is happening, the wave is triggered because of the failure of rock mass, and patterns of transient deformation is going to move radially away from the location where the disturbance was triggered because of the failure of rock mass. So the waves could propagate as body wave, where stress waves propagate through the interior of a three-dimensional object. Examples are P waves and S waves. Or they could propagate as surface waves, where stress waves propagate through the surface of a three-dimensional object, examples being Rayleigh waves and Love waves. Now P waves, how they are developed, how they are generated is indicated on this particular animation. Here we actually hit a series of elements in that manner, in the manner shown by the arrow there. Then what is going to happen, a deformation wave is going to propagate in that manner. Here the propagation direction is like that, and the particle motion is parallel to the propagation direction. It is the fastest wave, so that is the first to arrive from the focus to a particular site. Then S wave is triggered by heating, it can be generated by heating in a transverse direction those same set of elements what we considered before, and if a sudden deformation is triggered because of that, a deformation wave is going to propagate in this manner. So, this is called the S wave, and here you have got the propagation direction like this, but the particle motion is taking place in a direction transverse to the direction of propagation of the deformation wave. It is slower than P wave, usually second to arrive at a given site, and it carries maximum energy during an earthquake. In Rayleigh wave, you have got retrograde particle motion taking place in an elliptical manner like that, and the extent of motion, actually intensity of motion, decays as you go down deeper from the surface of the earth. So, here you have got a particle motion, retrograde elliptic particle motion that decays with depth, and it is this particular wave actually travels the farthest. It does not decay as readily as P wave or S wave. Love wave is very similar to Rayleigh wave, except here the particle motion is transverse to the propagation direction, but here also the particle motion decays with depth. Now, ground motion is a sum total. It is actually a sum. It is essentially a combination. What you see is a combination of the effect of all the stress waves that we just now looked at. They originate at the location where earthquake is originally triggered, and when you measure the disturbance that is caused when the waves arrive at a given site, what you get is essentially a time history of random particle movement shown by time varying acceleration here in 3 orthogonal directions. These particle motions typically measured with accelerometer, and here I have also indicated the what is defined as the peak horizontal ground acceleration, or PHGA, on the plot of the acceleration time history in the north south direction, and acceleration time history in the up down direction. What you can see, the peak amplitude there is called the peak vertical ground acceleration. I have also indicated the interval between the arrival of P wave and the arrival of S wave, and that is given the term SP interval. Now, you can see that if you calculate the SP interval from the ground motion measured at 3 different sites, you can find out the location of the focus of an earthquake by considering the velocity of P wave movement within the rock mass, intervening rock mass, and the velocity of S wave movement within the intervening rock mass. And this is the way actually earthquake focus is fixed or located by instrumented information from several different sites on the surface of the earth. Now, you have to measure the strength of an earthquake. One of the ways to express the strength of an earthquake is the intensity of earthquake. It is essentially a qualitative measure of observed earthquake, observed damage. It decreases with distance. There are various scales used for this particular purpose, such as modified Mercalli intensity, MMI, and it goes from intensity 1 to intensity 12, or Rossi-Forel scale that goes from intensity 1 to intensity 10. Intensity 1 is the weakest earthquake, whereas intensity 10 or 12 indicates the strongest shaking at a given site. An example is shown at the bottom bullet on this particular slide. For example, in the MMI scale, intensity 3 indicates it is very similar to vibration due to a moving truck. Intensity 8 it denotes an earthquake which causes tumbling of structures such as chimneys or smokestack, and intensity 12 represents complete destruction of structures in the given site. Earthquake magnitude, on the other hand, is an instrumental measure of energy release. This is independent of focal distance. There are various scales once again, such as local or Richter magnitude. It is denoted with M subscript L, that goes from 0 to 6.75. This scale saturates at a magnitude of about 6.75, or you could have moment magnitude scale which goes from 0 to 10. You should note that 1 point increase in moment magnitude scale signifies about 32-fold increase in earthquake energy release, and larger the magnitude, longer is the duration of earthquake, and greater is the epicentral intensity and PGA. Now let us summarize what we learned in the last two lessons. We looked at the origins and details of the theory of plate tectonics. We looked at the features of convergent, divergent and transform boundaries. We looked at evolution of continents through the geologic history and down into the future. Looked at description of earthquake process and list of earthquake characteristics. We wrap up this particular lesson with a question set. The first one is that what drives plate tectonics? Then second, why volcanism is not observed at all continental plate boundaries or convergent plate boundaries. I want you to explain the terms volcanic arc, magnitude and intensity. Then how earthquake epicenters or how earthquake hypocenters are located, and finally why subduction earthquakes are larger than those associated with seafloor spreading. Try to answer these questions at your leisure. I will give you my we will review these questions when we meet with the next lesson. Until then, bye for now. Hello everyone, and welcome back. Today we are going to talk about earthquake hazard assessment. We are going to emphasize actually those points which are related to the work of an engineering geologist. But before we get on with today's lesson, the subject matter, we are going to look back at the question set that I gave at the end of the previous lesson. So these are the questions. The first question that I asked was what drives plate tectonics. So basically what you have learned from the previous lesson is that the crust of the earth is composed of several different individual plates that are moving relative to each other, and these plates are essentially mobilized because of the circulation, or because of the convective action, because of the heat that is coming out from deep interior of the earth, within the underneath the surface of the earth. So the convection is actually driving the movement of the plates, relative movement of the plates with respect to or relative to